According to the FAA, air traffic control typically handles 44,000 commercial flights per day, and the one thing that 2.7 million passengers on those flights all have in common is, regardless of weather, they want to arrive at their destination on time. Keeping all those flights on time throughout the national airspace system puts a lot of pressure on key information about the flight is being transmitted to air traffic controllers via satellites and ground stations. As many on this call are aware, ADS-B out transmission is being mandated globally, and only ATC can see the information, which is why the industry is looking toward cockpit-based ADS-B in applications and how they can benefit airlines. We are joined today by Captain Dave Surridge, Senior Manager of Airspace Optimization for American Airlines, as well as FAA representatives Andrew Schutt, Project Lead for Avionics Agreements and the Surveillance and Broadcast Services Program, and Doug Arbuckle, Chief Scientist of the Surveillance Services Directorate in the Program Management Organization of the Air Traffic Organization, together with ACSS representatives Chuck Manberg, Technical Fellow, and Cam Morass, Program and Certification Manager for ADS-B in products. Together, they're going to talk through the ADS-B in Retrofit Spacing Evaluation Program and the benefits ADS-B in cockpit solutions will bring to the industry and worldwide. And now I will turn it over to the FAA.
Thank you, Bill. This is Doug Arbuckle from the FAA. I'll start out. And we're going to talk about ADS-B in applications. That's what I'll talk about, and then Andrew Schutt will follow with a description of the ADS-B in retrofit spacing evaluation. So the industry need for ADS-B in is around being able to increase NAS efficiencies with different onboard capabilities on the aircraft. The top part of the chart talks about applications that use equipment to leverage the efficiencies of visual separation in the United States. So the ADS-B in equipment can allow the pilot to maintain the visual separation from traffic during a visual approach and conditions that may where the pilot's vision may be impeded, such as night going into a busy metropolitan area, or flying maybe into the sun, or it's just a marginal visual day. We are also looking at being able to use the same equipment to allow the flight crew to maintain visual separation in conditions where we wouldn't currently allow those today, and I'll talk about that more on the next chart. And then at the bottom of the chart, we're also talking about an ADS-B in application that you'll hear referred to as interval management that allows, where the onboard equipment is computing recommended airspeeds that the flight crew follows, and that helps them manage the distance behind the aircraft in front of them. We use the word spacing here because this is not separation. The idea is that the spacing interval that's defined would be set higher than the separation standard. But what we're trying to do is we're trying to remove the excess buffer that often occurs in these kind of operations. So to talk about the first one, the visual separation benefits, this is a chart that shows what happens is a visual airport visibility across the bottom in miles, and then the ceiling in effect is the vertical axis. And so legal VMC is 1,003, the little red circle there on the chart. But quite often at most busy airports in the United States, visual operations terminate long before you get to that ceiling and visibility condition. And we've marked on here 5,007, which is not, there is no pure standard, but it's just sort of giving you an idea of, there is a minimum radar vectoring altitude that does drive what it is, and it's different at every airport in the United States. So this is just sort of an approximation. And so when you're in the top right corner of this chart, you're operating in what we call high VMC, or severe clear, depending on your terminology. And that's when the U.S. system operates at its peak efficiency. Controllers are assigning flight crews to maintain visual separation or follow the aircraft to the runway that they're, and so that's, and we don't have to maintain all the radar separation standards that occur when we get into the yellow zone. So in the yellow zone, usually visual operations are being suspended because the ceiling has gotten below the minimum radar vectoring altitude, and the controllers are now having to use IMC procedures to vector the aircraft into the runway. So the benefit space for what we call CAVs or ECAVs is in this yellow zone that we've labeled marginal meteorological conditions. It's not really a formal designation, but it's just for the purposes of discussing what the benefit pool is. So to the extent where we can pull the dark blue corner down closer to where the red circle is, that's the benefit space for using these tools. Then moving on to interval management. Interval management, the idea here is that the controller would assign a spacing goal to the flight crew, typically in time, but it could also be in distance if that's the preferred approach. The flight crew enters that information into their equipment, and then they can manage that on board the aircraft with the speed guidance that the equipment is computing for the flight crew. And that gives us very tight tolerance. We call it the IM tolerance, and it usually is on the order of plus or minus 10 seconds 95% of the time, or if you talk about standard deviations, it'd be 5 seconds, and we'll talk about that on a future chart. And there's different applications you can use this capability for. You can use it for aircraft that are arriving on the same runway. They're coming from different directions and merging at that achieve by point ABP you'll see on the chart there. And then that's for the same run, we call that same runway. Then there's also operations where you can manage your spacing relative to another aircraft that's on a dependent crossing or converging runway, or a dependent staggered operation. The ultimate case of that would be the San Francisco arrival on the 2.8s, and paired approach, which is really been designed for the San Francisco operation, because that's where your things are really getting close, and you see there's an offset, an angular offset on one of the parallels because the parallel arrivals are so close. So there's different application domains for this capability. Moving on to the next chart, what is the benefit of interval management? And it's pretty much as you reduce the spacing precision, then you get more aircraft that are arriving with a tighter tolerance, and so then you can in effect your target spacing becomes less. So if you take the peak of the red curve and you move it to the peak of the blue curve, that's your benefit, is what we call reducing the standard deviation or IAT sigma, which is the standard deviation of the inter-arrival time, the time between the two aircraft crossing over the runway threshold. And as you reduce that, increase that precision or reduce that dispersion, depending on how you want to look at it, your runway throughput goes up. And for this example that we showed, which is just math, right? You can get potentially up to 17 additional aircraft per hour versus the current baseline of the NAS, although we're not actually thinking that that's what we're going to achieve, but it just sort of shows what's hypothetically possible. And now I'm going to pass the presentation over to Andrew Schutt, who'll talk about the AIRS evaluation.
Thanks, Doug. Our AIRS evaluation project is a operational demonstration project that the FAA is hosting. We're collaborating with American Airlines and ACSS on this project. It's as I mentioned, it's an operational demonstration project to measure the value of ADS-BN capabilities using a retrofit solution. Specifically, the ACSS equipment that's being installed on the American Airlines aircraft for this project is integrated into the TCAS unit as well as the MCDU, and it has a supplemental display for ADS-B target identification. The overarching objectives of the project was to support the further development of ADS-B avionics and gather operational data in a live environment, as well as provide insight to inform future IM development. In the past, the FAA and airlines and the avionics manufacturers have worked on technical demonstration projects, but this one, what sets this particular project apart and demonstration is that it's using commercially available avionics permanently installed in aircraft on revenue-generating flights and using a large number of pilots and controllers. So we've had some of our subject matter experts in the FAA working with the industry to develop the MOP standards and to further develop some of the existing standards. That work has pretty much been done. What we're doing now going forward is, as American will be talking about some of the installations coming up here soon, but as we move forward, we'll start seeing aircraft with the avionics on board, and we can start validating the benefits, gathering that operational data. Specifically, the capabilities that we're looking at are AIRB, CAVs, and a limited set of the IAM capabilities that Doug just talked about. We also will be considering additional use of the CAVs equipment beyond what the MOPS standards had initially envisioned. We'll be just kind of considering those operational uses of CAVs, and I'll talk more about that as well in an upcoming slide. For this project, we're going to be measuring the benefits on those flights in the Albuquerque Center's airspace on westbound flights going into Phoenix. We'll record the results and generate a benefit analysis from that. And the project will take a couple of years that we'll be measuring the data. This has been a collaborative effort, as I mentioned before, between American Airlines, ACSS, and FAA. We have an agreement between us. American Airlines has furnished time on their simulator, coordinated with their pilots and trained them. They also will support the data collection, and they've done flight testing to get the certifications required. And then they're equipping their fleet of A321s for us to do this operational demonstration. ACSS developed the avionics in line with our project constraints and supported flight testing and certification. The FAA has provided a limited amount of material support and the project coordination, as well as interfacing with the different policy organizations in the FAA. And I also like to mention that we collaborate with our controller union, NATCA, which is a vital part of our project team in order to ensure the operational success of this. So Doug kind of gave you a brief description of the CAVs operation. So just a couple of key points to remind you: as pilots must acquire the lead aircraft out the window first, and then use the avionics as an aid when they're using the CAVs equipment. Normally, it is performed in VMC conditions on visual approaches. It does not depend on any enhancements to ground automation for the air traffic controllers, and there's no new phraseology or procedures required. So the point there is that as soon as the equipment starts appearing on American Airlines in their fleet, they can perform the CAVs operation at any airport that they want, as long as they've given that visual separation from controllers, and they can use that equipment. And we'll start again gathering some benefits from that. We'll start measuring some of the data from that. They did a test flight in September, and the operations approval is expected to be completed by January, so they can install the equipment and start working those in January. And I already mentioned that the CAVs can be used at any airport. So the benefit that we're looking for from the use of CAVs are a higher rate of visual ops, and it also may reduce go-arounds for those aircraft that are equipped. Now, I mentioned enhanced use of CAVs, so American has also asked us to consider looking at using the CAVs in less than VMC conditions. They'd also proposed that we consider using the CDTI. That's the display that shows the aircraft that they would be following on the display. It gives them the ADS-B end data. Using that to acquire the traffic to follow, and then setting this up in IMC conditions potentially. So the difference there is that it require air traffic to know who's got that capability. So there have to be some upgrades to the FAA's automation system in order to provide that, and also a new phraseology. So there's a little bit heavier lift for us to do that, but it's something that we want to consider. FAA's taken an incremental approach looking at that within the scope of this project to expand the envelope in which CAVs operations can be performed. as I mentioned, since the automation is required, then we would have to, for the demonstration project, we'd have to use some type of a workaround. So we'll have to work with our NACA controllers to come up with that kind of a workaround. But for a specific airport where we can demonstrate this, it very well may be feasible to do that as a trial. That's what we're looking at doing. I mentioned that there's a limited set of interval management capabilities that we're going to be measuring and validating benefits on. Again, some key points from previous slides. Pilots use these tools in the flight deck to achieve and maintain an assigned spacing goal behind a lead aircraft. It's for this project, it's going to be initiated in the en route airspace, but it could extend down into the terminal airspace at a later time in the project. Decision support tools are normally required for IM to determine the aircraft pairing and the assigned spacing goal. For this project, because those automation tools won't be fully in place before we start the demonstration, we're limited to two types of clearances, and that's a capture and achieve by is what we call them. And a capture is where an aircraft is just following another aircraft already, but they're not at the assigned spacing goal, so the controller will issue the assigned spacing goal. The pilots will put that information into their avionics, and the avionics will give them a speed to maintain, and then they will eventually slide into that spacing goal that we're shooting for. And achieve by is similar, except that they'll give them a point in space in which they want them to achieve a assigned spacing goal behind another aircraft. So the one aircraft will pass over that space, and then when the following aircraft hits that space, they should be at the assigned spacing goal behind the other one. So that'd be used like at the boundary between where the center hands off to the TRACON. Is a good achieve by point is what we call that. We had two particular arrivals in the Albuquerque's airspace, Ping 1 and Eagle 6, that they're going to be performing these operations on, and that's where we're going to measure our benefits. And as far as the IM operations goes, because of the training involved for air traffic, and we will have to, there'll have to be a certain number of equipped aircraft before we can actually start measuring those benefits, those aircraft pairs. This slide here, slide 17, just has a summary of the AIRS operations, the capabilities that we're looking at, the benefits that we expect to achieve, the avionics certifications for these different capabilities, and then the operational approvals that were necessary for operators to use them. And now I'll turn it over to Chuck for the ADSB Avionics Retrofit.
Thank you, Andrew. Well, folks, the year 2020 is finally upon us. ADSB out is now a fact of life. Good morning. My name is Chuck Manberg, and I'm a technical fellow at ACSS. I've been involved with ADSB technology for over 14 years and have witnessed the evolution of the technology from its infancy to today's current state. I'm here today to present the ACSS flight deck display evolution and briefly introduce some of the ADSB and airborne applications and their benefits. ACSS has leveraged its experience in airborne surveillance and ADSB technology to develop avionics equipment, enabling the deployment of ADSBN applications. ACSS was one of the first avionics suppliers to provide ADSBN solutions called SafeRoute and retrofit these solutions into commercial aircraft. ACSS first installed and certified SafeRoute on the UPS Boeing 757 and 767 aircraft in 2007, and then followed with additional equipage with airlines as shown on this slide timeline. Unfortunately, there was not enough targets of opportunity, therefore ADSB out equipped aircraft to obtain the ADSBN application benefits during that time span. Also during this time frame, industry standards and FAA advisory material were generated to provide guidance for consistent equipage performance for ADSBN. As the ADSB mandate approaches 21 days from now, Opportunities now become abundant for operators to take advantage of the benefits ADS-BN applications promise. Early versions of the ACSS Safe Route system utilized a Class 3 electronic flight bag, or EFB, as the display platform to retrofit aircraft with the ADS-BN cockpit display of traffic information, or CDTI application. CDTI provides the flight crew with the traffic situational awareness of the surrounding traffic, as well as display and control of information to support the ADS-BN applications. Also, a small numeric ADS-B guidance display, or AGD, was included in the flight deck panel as a complement to the CDTI, providing required ADS-BN application data in the forward field of view. The use of the EFBs for hosting the CDTI eliminated the need to require expensive upgrades to the primary flight displays in the retrofit aircraft. But one downside of the Class 3 EFB solution was the location of the CDTI, generally installed to the side of the main display panel, with only the AGD in the forward field of view. As time advanced, airlines began incorporating off-the-shelf tablets such as iPads as their EFBs. Hosting the CDTI and ADS-BN applications directly on these tablets are prohibitive due to the certification requirements for the applications. Therefore, a new cost-effective solution was needed to incorporate the CDTI in these aircraft. ACSS developed a retrofit CDTI solution that utilizes existing flight deck displays and supplements the solution with a graphical AGD. With the evolution of the FAA guidance material, ACSS utilized existing TCAS traffic display on the primary flight display to display ADS-B traffic using TCAS symbols, providing the relative positioning of traffic to own aircraft as a part of the basic CDTI capability. The CDTI solution incorporates the existing multi-purpose control display, or MCDU, to provide display of additional ADS-B information and flight crew interaction with the CDTI and ADS-BN applications. The addition of the graphical AGD, which provides directionality and application-specific information, the new CDTI solution provides ADS-B information in the flight crew's forward field of view and flight crew interaction that is more consistent with the current flight decks, such as interaction of the flight management system or in FMS via the MCDU. So, an example integration of the SafeRoute ADS-BN retrofit display system into the flight deck of an Airbus A320, A330 aircraft family is shown on this slide. The AGD is installed in the flight deck in a spare location that was previously occupied by a display no longer used. ADS-B traffic is shown on the TCAS display using TCAS symbology to provide relative position of traffic. Additional information associated with the display of traffic is provided on the MCDU. Also, the AGD provides directionality of the traffic and specific information for selected or designated traffic, lead traffic to perform spacing operations. This slide provides an example integration of the SafeRoute ADS-BN retrofit display system into the flight deck of the Boeing 7X7 aircraft family. Opportunity to install the AGD in these aircraft flight decks is provided by the fact that most aircraft OEMs and airlines are installing integrated electronic standby indicators, thereby providing an equivalent size panel opening to install the AGD. Now I'll talk a little bit about the applications themselves, and you'll see some example displays utilizing the new retrofit display system architecture. The most basic and foundational ADS-BN application is Enhanced Airborne Traffic Situational Awareness, or AIRB. AIRB improves the ability of the flight crew to identify where surrounding traffic is located relative to own aircraft along with the directionality and speed of the traffic. Additional traffic awareness information available via ADS-B are flight identification, ground speed, altitude, vertical tendency, and vertical speed. In current day flight operations, flight crews generate situational awareness by combining all available information such as out-the-window observations, TCAS traffic display, radio communications via controller-provided traffic advisories, and controller communications with other aircraft. With the addition of AIRB in the flight deck, the flight crew can see the location of the surrounding traffic similar to the traffic picture that air traffic controller sees, creating an environment of shared situational awareness and crucial see and avoid capability. The additional traffic situational awareness aids the flight crew in visual acquisition of traffic and aids in on separation operations. This increases the airborne traffic situational awareness, resulting in enhanced safety during flight operations. CDTI assisted visual separation, or CAVS, is a procedure that takes advantage of the traffic situational awareness provided by the CDTI and ADS-BN to maintain visual separation during reduced visibility approaches. Displayed distance and differential ground speed shown on the display on the right-hand corner to a designated traffic target are the primary information used in aiding maintaining visual separation. Visual approaches to an airport allow the aircraft to follow a preceding identified aircraft and maintain on separation to this aircraft as long as the airport or preceding aircraft is in the flight crew's sight. If the flight crew loses visual conditions due to deteriorating weather conditions or conditions when visibility is impaired by bright sunlight or nighttime operations, the flight crew contacts ATC, the visual approach is canceled, and ATC now maintains the separation. In general, arrival rates are higher when performing these visual approaches. CAVS provides the flight crews with the ability to maintain a visual approach in visual conditions, which reduces flight time, flight distance, and enhances airport capacity. Flight crew is allowed to use the CDTI to continue the visual approach in cases where traffic to follow is no longer visible out the window. The AIRS interval management application is a flight deck tool used to issue speed guidance to the flight crew for managing the speed of their aircraft to achieve and maintain an ATC assigned spacing interval relative to a designated lead aircraft. Interval management, or IM operations, begin with ATC providing spacing clearance to the IM aircraft that includes the designation of the lead aircraft, the desired spacing interval, and the point along the path to achieve the spacing. The flight crew will enter the information into the IM system via the MCDU and initiate the operation. The IM system will compute and display a speed required to achieve and maintain the desired spacing interval using the received ADS-B information on the lead aircraft. The flight crew will adjust the aircraft speed manually to the IM provided speed command to achieve and maintain that desired spacing. The benefits of IM are increased efficiencies by maintaining consistent low variance spacing between aircraft, resulting in arrival predictability and airport capacity increase. The objective of in-trail procedures, or ITP, is to improve the situational awareness and enable flight crews to perform desired flight level changes in oceanic and non-radar airspace. Concept takes advantage of the ADS-BN and CDTI to enable the climbs or descents in situations where the aircraft is currently blocked by traffic due to procedural separation standards. For example, in today's operations in the North Atlantic track system, aircraft are separated at required intervals. If the aircraft desires to climb to a more optimum altitude that requires a transition through altitude with aircraft positioned at standard separation, the aircraft would be challenged to make the climb. With ADS-BN and the display of the surrounding traffic information on the flight deck, a new IETP separation criteria has been established based on distance and ground speed to potentially blocking aircraft that enables the flight crew to know when to request an IETP climb from controllers to reach a more fuel-efficient altitude. It's my pleasure now to introduce Captain Dave Surridge of American Airlines, who will discuss the AIRS development, some planned trials, and flight tests.
Thanks, Chuck, and it's a pleasure to be with this group and talk to everybody about a really exciting new technology that we're trying to bring to the NAS, and all the benefits that we think that we can achieve from that. We're excited at American to be a part of this new state-of-the-art technology. There's a lot of work to be completed, but we are confident in the ACSS system and the FAA's capabilities to make the changes necessary to bring this new technology to market. What led to American's decision to look at the new and changing ADS-BN technologies was in particular the ADS-B out mandate that it will now be in place in about a month from now. This really allows for multiple capabilities and opportunities for our airline and other airlines alike to get more efficiencies out of the hub operation and also enhance some of the safety for our pilots. We worked hard with ACSS for close to a decade now to develop this into a very usable system that also makes a business case for operators. In that time, we've learned that a lot about proper architecture. In the past, we had EFBs, Class 3 EFBs that were sitting on the side that were prone to maintenance issues and breaking down. We went back to ACSS, and they came up with this new architecture that really incorporates everything in the flight deck and is what we think is a home run. We worked with our pilots, our union, to look and make sure that we get the proper look and feel for the technology that's going into the flight deck. And ACSS did a great job of listening and applying what the pilot wanted with their own knowledge of the design. We ended up choosing the Airbus 321 as the aircraft to initially equip. We are scheduled to equip all of our 321s, so that's a total of 319 aircraft. These aircraft have a big presence in our hub-to-hub operations, and we felt that is where a lot of this technology will really have a benefit for our airline. We've talked a little bit about CAVs. Some of the business case for CAVs, we did at one point, about 8 years ago, have a small set of 330s that had similar technology than this new technology, but it was ADS-BN, and we did do CAVs operations. We were able to gather some data from those CAVs operations, and what we found is that close to the airport, we were shaving off anywhere between 52 to 134 seconds off of each flight, and we saw a reduction in time in addition to that. The technology allows the pilots to know how much faster that they're going than the aircraft in front of them. And it also gives them a very good idea of how much distance. As time goes on, we believe the pilots are going to be able to use this new information in the flight deck to make better decisions, and that is going to increase safety, increase efficiencies, and also one of the things we're hoping to see is a reduction in go-arounds. So the benefits of ADS-BN aren't 100% known at this point, but we do know, just as you look at aerospace and what we do know, that if you can get a reduction in spacing, if you can get higher throughputs, our customers are going to be the ones that benefit from that. And we're hoping for a more consistent operation for the airline through runway rates that are maintained longer when the environmental conditions change, and reducing variability within our flights due to that. For the pilots, we're looking for more information coming in to the flight deck, and that will allow for better situational awareness, better decisions for the pilots, and we believe in an improvement in the safety of our airline. On the ground, there are also some improvements that we will see, given the fact that we'll be able to see other aircraft that are on the ground, our proximity to those aircraft, in addition to everything else that the pilots are starting to, the information the pilots are starting to get on their iPads, using current technologies with GPS. So we did a couple flight tests, and they went very well, better than expected. Personally, there is always a little bit of concern when we talk about the workload that the pilots have, and whether or not that workload is going to go up, especially in the descent and the terminal environment. The good news was that the algorithms on this system worked better than I had expected, and better than what we had seen in the simulator. The amount of changes that we needed to do to maintain literally a few seconds in the spacing delta. So we were holding about 120 seconds behind the aircraft in front of us, and the system was able to maintain that tight interval within a few seconds of each other. So it was pretty exciting, and the amount of work that I had to do was very minimal. Literally, just a couple times I had to change the airspeed to maintain that interval. So they both went well. We did find some issues, minor issues, with some speeds with the MCDU, and we worked with ACSS after the first test, went through them. ACSS was able to find a fix, and everything on the second test worked great, and everyone was impressed with the improvements made by ACSS. I'll go ahead and give this back to Cam for final comments.
Thank you, Dave. I'm Cam Lass. I'm with Program Management at ACSS. Thanks again for that intro, Dave. So this webinar, the timing of this webinar is not a coincidence. It comes at a time when we've completed the software development, software certification, and the aircraft certification. We are now poised to begin aircraft installs, and then move on to the large-scale operation that Andrew had talked about. So again, the certification is in place for the American Airlines A321 fleet. We are looking at beginning installations in mid-January. That will be the first aircraft activation. We then have approximately a 4-year installation plan, 4 to 5 year installation plan to address the full equipage of the 321 fleet. We are actually going to begin collecting data, of course, during the first aircraft operations. We have baseline data that's been collected that we will be comparing that against, with the intent of providing a benefit analysis and a report out to the industry in the 2022 timeframe. And this will be under the AIRS working group that's been established to support this activity. The next slide here is additional activity that's going on with ADSBN. So we are involved with numerous industry focals, FAA, Airlines, other entities such as MITRE,